Well, good morning for those of us in the Central Time Zone. Just good afternoon to those of us on the Eastern Seaboard. This is the March 2026 edition of the CR2C2 seminar. We're super pleased to have Dr. Chakraborty from the University of Tennessee and Dr. Getahun from North Carolina A&T. And this is a particularly interesting project, right? Because one of the things that we've wanted to do with CR2C2, and as we move through the successive years and project conception, development, and completion, as the UTC runs its course, is moving towards implementation, moving towards deployment, and that sort of thing. So I think to the extent that the center is focused on rural transportation, I think this is a very exciting, very interesting topic that takes things in the simulation environment to see how we can make sure that the rural environments are most ready and accepting, accommodating of autonomous vehicle applications, which I think is something we're all working towards in some shape, form, or fashion, whether technology, policy planning, and that sort of thing. So I think this is going to be a great talk. With that, I will turn it over to our speakers, and thank you very much for doing this for us.
All right, should I get started? All right, then let me share the screen and let's see. All right, we have the right screen, hopefully. All right, did it work? All right, good. Well, that's an achievement in itself. We got the right screen up and running. Well, thank you, Stephen. Thanks, Ali. Thanks, everyone, for being here. So I'm going to talk about our project R24, the CRTC2 project. It has ended after 1.5 years of development, and I think we have some exciting things that we want to share today from that project. So I am Subhadeep Chakraborty. My co-PI is Dr. Katak, and Joe and Zach are the students who primarily worked on this project. Both of them have graduated. Both of them are well placed. So, from a workforce development point of view, I think we are all pleased to see that. So we are going to talk about enhancing automated vehicle operation and safety on rural roads. And this will be a very vehicle in the loop, simulation heavy kind of development talk. So hopefully, there will be something of interest to everyone, and we can kind of connect, once we are done with this. And I'll be hopefully, on time, because we have another exciting talk after this. All right, so there are challenges to rural safety. We all know this, that higher speeds lead to increasing crash severity in rural driving. The roadway infrastructure, sometimes there are fewer safety features and more opportunities for roadway departure type crashes. Emergency response takes longer because distances to hospitals and trauma centers are longer, so it leads to slower response times. So that kind of increases the problem after a crash. So with all this in mind, the question that we are asking, and all of us are asking, is how do autonomous systems play into this? In this environment, does introducing autonomous systems make the system better, faster, more efficient, safer? But before we can get there, what are the challenges that autonomous systems face in operating in rural environments? So the goal is to develop a robust, safety-centered solutions that will enable these autonomous vehicles to navigate these rural environments with the same level of reliability that they do in urban corridors, right? All right, so AVs do struggle in rural areas, and for a variety of reasons, because one, most of the infrastructure, most of the funding, most of the data sets are centered around urban settings, right? Where we have much more structured environments. We have high fidelity digital maps. The infrastructure is much more dense. So when we go into much more open rural countryside, there are not that many even salient landmarks from which the point cloud, the LiDAR point clouds can be referenced. But that means, we cannot even localize ourselves properly. So we have GPS and IMU, but we do not have that, way to localize ourselves. So along with that, there are connectivity gaps. There is adverse weather. Weather can be pretty significant. It can make the LiDARs and the cameras misinterpret information. unstructured rural roads, lack of lane markings, so on and so forth. I mean, many of the talks in CR2C2 kind of have already mentioned these things. So these all challenge the AV perception, planning, and control pipeline, right? And our plan is to establish a digital twin-based simulation and testing infrastructure that will enable safe, reproducible evaluation of all these things, the perception, planning, and control modules. We can, something that will let us make and define our own complex rural environment, and then probe each and every individual of this pipeline and make sure we understand where the faults are originating, how they are kind of moving down the pipeline, and ultimately how they're manifesting in unsafe driving. So that is our objective. In doing that, these are the 5 subtopics that we will hopefully at least be able to touch on a little bit. 2 major theoretical developments that we have done. One is the Genesis RL. We will talk about that. So that instead of blindly looking for edge cases, this is kind of a much more concrete way of finding those stress cases that make the AVs fail. And the other one that will be that we'll discuss today is something called PEM, which will be a way to characterize the error when we shift domains from virtual or synthetic to real. Right? So we'll talk about those things. Before we do that, let's start with something very simple. We are all familiar with this AV pipeline. So there is the environment, which is at the mercy of weather and lightning, other cars and pedestrians, and partial occlusions, road type, geometry. All of that is sensed, and usually the sensing is done either by a camera-only system, we will talk about that, or it can be sensed by cameras, lidars, and radars, and then that goes through a perception block, which gets an idea of this environment, and then it uses a variety of sensors like the lidar point cloud, like I mentioned, along with GPS and the odometry from the wheels, and combines all of that in localizing itself, and then it does path planning depending on what it senses around in the environment. It goes into the lower level controller, the controller issues control signals, it goes into the lower level, some kind of a drive-by-wire system which has a underlying PID or MPC controller, which then gives commands to the actuators. The car moves, the whole process continues, and we have a autonomous vehicle. So that's kind of the overall pipeline. Now the question is, how can we simulate it in a safe lab environment while being still true to the environmental attributes, right? So there are 2 kinds of things that we will talk about today. One is the software in the loop setup. So this one is fairly simple. Our simulator is built on the Carla, based on Carla. Everyone uses Carla. So inside Carla, the cars, the kinematics and dynamics are based on their physics model, right? And once we have the Carla simulator set up, it produces these frames which are giving information to the car controller, the brains of the car, which in our case is the Open Pilot controller. So the Open Pilot grabs these images, camera images from Carla, and then it does its entire stack of AI-based model for figuring out how far things are from it, such as relative distance to the car in front of it, relative speed of vehicles. It uses a perception model called Super Combo and gets all of this information. It kind of works as a camera as well as a pseudo radar. So it knows what it's looking at and how far it is from just one camera image. So it uses the Open Pilot controller, and then it issues control commands to the Carla simulator. The car moves forward, and we have a entirely software-based simulation platform in which we are now free to inject any kind of disturbances that we want. Right. Now, the improvement in this is our major contribution, I would say, for this project, where we worked with a local company to develop this system that lets us put a car on a dynamometer, but at the same time lets us swivel the front wheels. So that essentially gives us an unprecedented amount of control on what we can do with the car, right? So we have the same Carla simulator. So we are creating and generating this synthetic environment, synthetic images. Those images get processed by the Open Pilot Super Combo perception system. And now, instead of just relying on the Carla physics engine, what we are doing is we are sending that information to the actual through the through the CAN bus to the ECU of the car, and generating actuation comments for the car itself. So remember that the car is sitting on the dynamometer, and when it receives those actuation commands, the wheels really spin. The steering actually enables the car to swivel forward and like right and left, and those things are then transferred through an inverse kinematics model, which is essentially just a bicycle model for the car, which lets us know how far the car moves forward in the synthetic space, and that lets us update the position of the ego vehicle in simulation, and which changes the frames and makes the whole simulation kind of move forward in time. So this is the novel vehicle in the loop setup that we are really proud of. We worked really hard to get it up and running. There is considerable hardware innovation that was needed to make this happen. And obviously, what this lets us do is have a real vehicle dynamics that we can access. And at the same time, we have a safe environment because the car is tethered, right? So we can put anything inside the Carla simulator. We can put a pedestrian that darts out in front of the vehicle.
Okay. I found this on the web for this theory actually enables the car to swivel forward like right and left and those things.
I did not. I don't know if you heard that. That was Siri suddenly activated. Anyway, so we have this whole vehicle in the loop setup where we can generate any kind of situation, safe or unsafe, and still be in the safety of the lab. There are some other more subtle advantages, such as we can essentially know beforehand the ground truth of the scenario, right? We know exactly which pixels are covered by the pedestrian. We know which pixels are covered by the car in front of it, so that we have the ground truth information without any kind of manual labeling of data. So with all of that information, with the ability to change any of these parameters, one by one and keep it consistent, we now move to the description of what it actually is able to do. I'm going to skip the model in the loop setup for in the interest of time. All right, so this is the Open Pilot controller. I kind of mentioned this, that it uses a pre-trained perception model called Super Combo. It uses only vision, kind of like what the Tesla does. It can get the lane trajectory, it can get lead vehicle estimation in terms of how far away it is, the relative distance and the relative speed. And incorporating controller and VIL setup, we can kind of simulate any kind of modalities for edge case discovery. So here's a small video that lets us look at the hardware component that lets the car swivel the wheels. All right. So you can see that it has a fairly significant range of motion. It does not run too fast because we want to be safe, so we kind of restrict it to like 25 miles an hour and not more than that. But it is enough of a range that lets us do any kind of driving. Maybe not like a parking lot maneuver, but at least definitely right turns and left turns at intersections, lane changes, any kinds of behavior like that. And highway is of course easier because the range of motion needs to be smaller. All right, so these are some scenarios that we looked at. The first one is fairly simple. There's a stopped car and our ego vehicle proceeds towards that car and then has to stop behind it, and the car following is a simple car following. There's a car in the road. Our car has to follow a lead vehicle in different kinds of situations. Now the complexity and the interest obviously comes from our ability to change this situation, right? We can make it night, we can make it day, we can make it foggy, rainy, snowy, whatever we want to do. So here's an example of a very strange kind of, probably not completely realistic example that we looked at. So we made the car, and the left video that you're looking at now is the car on the dynamometer, kind of like the setup that we showed you before. So it is proceeding directly towards the car that is facing our vehicle. So this is not a normal situation that you will encounter, but it can happen. Maybe that car got into a wreck and got turned around. And just because of that little trick, because the car is not trained with enough images of directly going to a car, towards a car that is facing our ego vehicle, it goes and crashes into it. The next one, it does a lot better because it's a more standard kind of operation. We did this experiment on an empty parking lot, more for the purpose of calibrating our dynamometer with a real vehicle on an outdoor environment, and it works perfectly. It recognizes the car, it stops nicely behind it. So this kind of tells you, the ability that we have of making the car believe something that is not exactly actually out there, right? So we can kind of create this augmented reality for the vehicle and make it behave appropriately or not, depending on whether it does a good job. And the things that we are going to look at in trying to kind of have metrics for good or bad behavior, these are fairly simple. The first one is the time to collision that everyone knows and uses. The next one is a slightly more specific metric for us. It's the mean detection ratio. So it tells us how far away our estimate of the vehicle is from the actual estimate, from the actual distance of the vehicle. So, if dr is essentially 1, that means it is estimating the distance correctly. If dr is less than 1, it means that it thinks the car is closer to us than it actually is. And dr greater than 1 means that the car is actually closer, so our estimate is farther, okay? So obviously dr less than 1 is okay because we are being conservative and we are going to stop with plenty of space. Dr greater than 1 is a problem because now we think that the car is farther, but actually it is closer, right? So 1 is where everything is fine, greater than 1 is bad, less than 1 is good. So for different kinds of situation, whether we have sunset or noon or glare, different kinds of cars, colors of cars, shapes of cars, so on and so forth, we have done these experiments and we see that the data is nicely clustered. Some of these are over here, so that the time to collision is high, and the time to collision is 0 means that we actually went and crashed, right? So this is a fairly good indicator of, and this is all with real vehicle dynamics on the dyno, right? So we have now a way to measure, like, if my perception system behaves like this, then down the line, after it goes through all the trajectory planning and the controller, there will be an ultimate end effect of collision, right? Now we went one more step and said that, wait, let us now move or change our, the settings of the simulator and just start adding a little bit of fog into the system. As we increase the percentage of fog, we are also looking at what effect does it have on the perception system, and that dr, the ratio that we were talking about, how is that affected? Now we know that greater than 1.2, if you go back here, greater than 1.2 is really bad because that's when the car is making such a huge mistake that it ends in collision. And here we can see if this 1.2 is the line. So if the fog percentage gets above a certain level, there is no hope. Essentially, we are going to crash. Now, these fog percentages do not have an actual numerical meaning, of course, but they can be correlated to actual amount of fog in the environment, in the real environment, right? Similarly with the position of the sun. Once the sun angle goes all around the car, depending on the shadows and the glare, there are places where the car struggles, and we can find it out from the simulations. So this was one of the major objectives that we kind of could do, which is to have a whole reliable vehicle in the loop setup that can ingest these different kinds of environmental flaws and react to it, and we can measure and determine which are the more difficult ones. But we all know that just being able to find out what happens is not enough, because that's more like an anecdotal kind of exercise, right? I mean, if we say, like, let's try this and figure out what happens, let's try that. So obviously that's not enough. What we want is a more concrete, methodical way of finding out how we can find those difficult to deal with situations. So for this, we created this Genesis RL, which is an RL based supervisor, which is a core component of our safety validation pipeline. And it's designed to systematically generate those naturalistic edge cases. Okay. So if you look at it at a high level, this Genesis RL, it reframes edge case discovery as a sequential decision-making problem, essentially. So it's not interacting with the vehicle directly, but with the environmental parameter space. By that I mean that this external DRL agent, DRL stands for the Deep Reinforcement Learning Agent, it can control the knobs that will change my environment in Carla. Okay, so let's suppose one knob is fog, one knob is rain, one knob is the infinite position of the other vehicles around it. So this is like a infinite dimensional possibility space that we have handed over to the DRL agent and said that, hey, can you find a manifold in this infinite dimensional space where the car is going to have the maximum trouble, right? So that key innovation is the system level safety objective. So that's embedded in the reward formulation, right? So if you look at this, I talked about how it kind of can change these knobs over time. It can increase the fog density, it can modify the sun angle, it can introduce rain accumulation, and these adjustments lead to a progressively degraded sensing condition. Okay, and it finds the manifold that leads to the most difficult and challenging environment for the AVs to work in. So I mean, we can understand how important it is to be able to do that, because otherwise we are kind of blindly random walking in an infinite dimensional possibility space and trying to figure out what is the worst situation that we can give our cars to try, right? So that's kind of the idea here, and it's probably there's not enough time to really go into the details of the results, but that you can see that we can generate these kinds of problems for the car, leading to collisions at higher speed and different kinds of ways that the car reacts. Okay. It can also generate these edge cases, and that's another thing that we wanted to do, which is not to only look at these violation scores from a perception standpoint, but actually to look at what it does from a rule book violation standpoint. So we have a rule book score that determines how good the trajectory was, whether there was a crash, whether there was a near crash, and use those to train our DRL agent that leads to the least successful. It's funny because if the DRL agent is successful, that means our car is unsuccessful, right? So we want to find the most challenging cases for the car. So that was kind of the point of this whole exercise. So this worked out pretty well. We have a paper on this, and that's there at the last slide as well. But the obvious question that everyone is going to ask is now that, okay, so this works pretty well, but you're still working in the simulation domain, right? So there is an obvious translation or a shift when you work with real data and real camera images. And we thought about this and said that one possible way, obviously, is to make the simulations look as perfect as possible, right? So we can spend years trying to get a simulator to exactly mimic a physical camera. But we then decided not to do that. We said that, what if we do not need to do that, but we have a better way to model the error itself that comes into the picture once you're using real perception models. So that is the idea behind this PEM, or perception error models. Okay, so let's look at this for a little bit. Let's suppose the camera is looking at a real vehicle, right? And let's suppose the green boundary is the actual bounding box surrounding the vehicle. And you know that in the available data sets like Kitty or Nuisance, this has been done manually, meticulously, frame by frame. Someone has sat down and actually drawn these boundaries. Now, when you send this picture to a perception system like SuperCombo, it makes an error, and that error is a function of many things. It is a function of how far the car is, what the environmental conditions are, how fast the car is moving away or towards, the orientation, this and that. So this y hat, which is what the perception system actually outputs as the model output, is maybe this. This is obviously just a demonstration. Is the orange box. So the idea that we have for this PEM is, can we model the error? Because if we could model the error as a function of all these parameters, a deep learning model, then we can use the ground truth, which we always have because we are working with a simulator, so we know the ground truth, right? If we could take that ground truth and add that modeled error term, then we can mimic what the real perception system, the real camera would see. So that is the entire idea. For doing that, we had to go through these, very convoluted exercise of, working with real time series data, time series generative adversarial networks. We kind of developed this new type of generative adversarial network called FETSGAN. We came up with a new first time above threshold kind of different ways of making this FETSGAN really work for our purpose. But that is not important. What is important is the idea that this perception error model is modeling the error that exists between my real perception system output and the ground truth, right? So this is the experimental setup. Again, it's very simple. You have a vehicle that is, in front of us, and it can be either a leading vehicle moving away or a stopped vehicle that we are going towards. And, we worked with the PEM model. We tested it, to the nth degree, and it seems that, just give me 1 second. So it seems that both for the lead distance error and the lead speed error, the PM is doing pretty well. All right. So the close agreement between the real statistic and the PM statistic across all bins. This demonstrates that the PM quite successfully captures not only the mean, the central tendency, but also the variability of perception errors. Okay. And there is an extremely high distributional overlap, about 99.5% for distance and 99.77% for speed, and very low Cohen's d value. So Cohen's d value essentially measures how different distributions are, but it's the distance between them. And anything less than 0.2 is essentially acceptable, but we have really much lower than that. So it indicates that there negligible statistical divergence between the synthetic and the real error distributions. So this is perfect. I mean, because now we have a way to run simulations, use the ground truth, and essentially use the error model to mimic real camera systems. Right. All right. So I'll skip this one. Essentially, same kind of results, and these are some specific results that we did for rural environments. The others were kind of generic, so it could be rural, it could be urban. Here we kind of made it more complex because, as we know, there are different kinds of specific attributes like vehicles quickly moving in front of the car. We couldn't find a tractor in the town 7, the rural car lot, environment, but we thought that SUV would be good enough, so we did those kinds of tests and had a bunch of results that show that essentially it works pretty well. So it gives us an idea of how the PEM and the Genesis work together to develop these edge cases and what the car does in response. Right? And I think that's the last result slide, and we can quickly go over the product that we have and the publications. And I'm sure that this will be available for everyone. So if anyone wants the papers, they can download them.
Great.
All right. Last thing, Ali, don't stop me, please. I want to acknowledge the fantastic work that you guys are doing. For keeping the center alive and for all these opportunities, and also our appreciation for Dr. Kevin Hislip, because some of the development that we did in the lab are also partially funded by some other sources. So that, and with that, yeah, almost on time. Thank you.
Great.